The success on April 28 was followed by additional combat deployments throughout May and June. On May 1, VPB-109 achieved another confirmed kill, sinking a second small Japanese vessel off the coast of Borneo. The attack followed the same pattern as before: detection at long range, release beyond anti-aircraft range, autonomous guidance to impact, and immediate departure of the attacking aircraft. The crews were developing confidence in their new weapons, learning to trust that the missiles would perform as designed without requiring any guidance after launch. This fire-and-forget capability represented a psychological shift for aviators trained to follow their weapons all the way to impact, to make last-second adjustments, to actively pilot their attacks through to conclusion. The most significant engagement came on May 28, when aircraft from VPB-109 attacked a Japanese escort vessel near Okinawa, where American forces were engaged in one of the bloodiest campaigns of the Pacific War. The target was the Kaiboken-class escort Aguni, a proper warship rather than the small patrol craft that had been the previous victims. The guided missile struck the vessel, causing substantial damage, but Aguni survived. The ship managed to limp to port, where it remained for the duration of the war, too damaged for effective repair, but not completely destroyed. While not technically a sinking, this attack demonstrated that the guided weapons could successfully engage defended naval vessels under combat conditions. One final confirmed success occurred on June 18, when VPB-109 sank another patrol vessel. Additionally, squadron records indicate at least one instance where a guided missile destroyed a land target, an oil storage tank, proving the weapon's versatility against stationary objectives. These combat successes, modest though they were in absolute terms, represented proof of concept for autonomous weapons. The technology worked. Machines could find and destroy targets without human guidance. The age of smart weapons had begun. The other two squadrons equipped with these missiles, VPB-123 and VPB-124, achieved no confirmed successes during their combat deployments. Their after-action reports catalogue a litany of technical problems and operational challenges. Radar seekers confused by radar returns from land masses locked onto coastlines instead of ships. The humid tropical environment degraded electronic components despite improved sealing. In congested waters with multiple potential targets, the missiles sometimes locked onto the wrong vessel or failed to discriminate between friendly and enemy ships. Crews frequently chose to jettison their weapons without attempting attacks rather than risk bringing armed, potentially unstable missiles back to their bases. These failures were as instructive as the successes. Post-war analysis conducted by the Joint Army-Navy Assessment Committee examined the complete combat record and concluded that the weapon's effectiveness under actual operational conditions fell well short of what testing had suggested. The missiles worked beautifully when attacking isolated targets in open water under clear skies with all systems functioning perfectly. They worked much less reliably in the messy reality of combat, where targets were often near land, where weather interfered with radar performance, where electronic components failed due to humidity or vibration, and where the fog of war made target identification difficult. Yet even this mixed record terrified Japanese naval personnel who encountered these attacks. The Imperial Japanese Navy had entered the war with sophisticated understanding of naval combat. Their crews trained extensively in visual gunnery, night fighting techniques, and torpedo operations. Their tactical doctrine emphasized aggressive action, precise coordination, and warrior spirit. None of that training, none of that doctrine, none of that spirit offered any defense against weapons that killed from beyond visual range without human guidance. The fundamental assumptions underlying Japanese naval warfare had been rendered obsolete by technology they couldn't match and barely understood. To truly grasp the significance of these guided weapons, one must understand the vast technological chasm that had opened between American and Japanese capabilities by the final year of the war. Japan had started the conflict with certain technological advantages. Their Type 93 torpedo, known to the Allies as the Long Lance, was arguably the finest naval torpedo in the world, with greater range and reliability than American equivalents. Japanese optical equipment for naval gunnery was superb. Their aircraft carriers had pioneered certain design features that other navies later adopted. In the early years of the war, Japanese naval victories often resulted from technological advantages as much as from tactical skill. But while Japan refined and optimized existing technologies, America invented entirely new categories of weapons and sensors. The autonomous missile incorporated miniaturized radar, analog computing, gyroscopic stabilization, automated control systems, and integrated them into a package that could operate reliably under combat conditions. Each of these components represented cutting-edge technology. Integrated together, they created a weapon system that was quite literally incomprehensible to Japanese engineers who hadn't followed the same development pathways. When Japanese technical specialists examined captured American equipment, they could identify individual components. They understood that vacuum tubes amplified electrical signals, that servo motors converted electrical commands into mechanical motion, that radar sent out radio waves and detected reflections. But understanding individual components didn't translate into understanding how those components worked together as integrated systems. The systems-level thinking, the ability to design complex assemblies where multiple technologies worked in precise coordination, represented a different approach to engineering than Japanese industry had developed. This gap reflected fundamental differences in industrial philosophy and capability. American manufacturing had fully embraced mass production techniques pioneered in the automotive industry. Standardization meant that components manufactured in different factories could be combined interchangeably. Quality control systems ensured consistency across vast production runs. Design for manufacturability meant that engineers creating new weapons considered production requirements from the earliest stages of development. The result was an industrial base that could produce complex weapons at scale, taking revolutionary designs from prototype to mass production in timeframes that would have seemed impossible to Japanese observers. Japanese industry, by contrast, retained more artisanal characteristics. Skilled craftsmen hand-fitted components, compensating for variations in manufacturing through individual expertise. This approach could produce items of exceptional quality in small numbers, but it didn't scale effectively to mass production. More critically, it meant that advanced weapons requiring tight component tolerances and precise system integration were extraordinarily difficult for Japanese industry to manufacture even in small quantities. The guided missile, with its demands for precisely calibrated electronics and mechanical systems, was simply beyond Japanese industrial capabilities to produce. By 1945, these industrial disparities had reached crisis levels for Japan. Fuel shortages meant naval vessels often couldn't sail. Ammunition quality had degraded as raw material shortages forced the use of substitute materials. What little radar equipment Japan had deployed frequently failed due to lack of replacement parts and inadequate maintenance capabilities. The technological gap wasn't just about having more advanced weapons. It was about having a functioning industrial base that could continue producing and maintaining equipment while simultaneously developing new technologies. America could do all of this. Japan, by 1945, struggled to do any of it. The guided missile program embodied the American approach to these challenges. Behind the weapon itself stood thousands of scientists and engineers who approached warfare as a problem amenable to systematic solution through research and development. Dr. Hugh Dryden, the program's technical leader, thought about the project in terms of aerodynamics equations and control theory rather than naval tactics. His team included specialists in fields that had barely existed before the war began. Servo mechanism design, analog computing, radar technology. These were emerging disciplines where practitioners were literally writing the textbooks as they worked on practical applications. On the Japanese side, naval officers trained in traditional warfare doctrines found themselves facing enemies and weapons that negated everything they'd learned. The emphasis on aggressive tactics, warrior courage, and spiritual strength meant nothing when death arrived from weapons fired beyond visual range by aircraft the defenders never saw. The samurai traditions that informed Japanese military culture, with their focus on personal combat and warrior honor, had no answer to American industrial warfare. There was no opportunity for courage when the attack came from an empty sky. There was no opponent to face when your ship exploded without warning. The very meaning of naval combat had been transformed in ways that Japanese naval tradition couldn't accommodate. The psychological trauma inflicted on Japanese sailors who survived these attacks was uniquely disorienting. Death in battle they understood and accepted. The willingness to die for emperor and country was drilled into every serviceman from their earliest training. But this wasn't death in battle as they understood it. This was death from invisible weapons that gave no warning, no chance for response, no opportunity to demonstrate courage or skill. Survivors reported profound confusion, a sense of helplessness, and a feeling that they faced something fundamentally beyond normal warfare. Some described it as fighting ghosts. Others used supernatural metaphors to explain what had happened, because their mundane vocabulary for combat couldn't encompass the experience. While America developed automated weapons that removed pilots from danger through technology, Japan responded with the ultimate opposite approach, the kamikaze program. Where American engineering sought to replace humans in dangerous situations with machines, Japanese doctrine turned humans into components of weapons systems through ideology. This contrast perfectly illustrated the civilizational differences in how the two nations approached warfare by 1945. The kamikaze program was initiated by Vice Admiral Takejiro Onishi and explicitly framed as a response to American technological superiority. Japanese leaders recognized they couldn't match American industrial capacity or technological innovation. The kamikaze doctrine argued that Japan possessed something America lacked: warriors willing to sacrifice themselves completely in attacks that guaranteed their deaths. A human pilot guiding his aircraft in a suicide dive, the logic went, created a missile more accurate than any mechanical guidance system and far more reliable than temperamental electronics. The human brain, the argument continued, was a more capable guidance computer than anything built from vacuum tubes and servo motors. This parallel development of radically opposite approaches defined the final phase of the Pacific War. American sailors facing kamikaze attacks experienced terror similar to what Japanese sailors felt when attacked by guided weapons. In both cases, death arrived too fast to counter from attackers who couldn't be deterred. Kamikaze pilots couldn't be frightened away by anti-aircraft fire because they had already accepted death. Guided missiles couldn't be deterred for the same reason. They had no fear to exploit, no survival instinct to manipulate. The symmetry was striking, even as the underlying philosophies were mirror opposites. Yet while kamikaze attacks represented desperate innovation within Japanese capabilities, the guided missile represented American exploration of new technological frontiers. Kamikaze tactics were a last gasp of martial tradition being crushed by industrial modernity. They demonstrated courage and commitment, but pointed toward no future. There was no technological development pathway that led from kamikaze to something more advanced. The guided missile, by contrast, was clearly a first step towards something more sophisticated. Even with all its limitations, it pointed toward a future where weapons systems would become increasingly autonomous, intelligent, and capable. The guided missile operated within the larger context of America's systematic strangulation of Japanese maritime operations through overlapping technological advantages. Operation Starvation, conducted by B-29 bombers dropping sophisticated magnetic and acoustic mines in Japanese waters, had by April 1945 virtually eliminated coastal shipping. These mines were themselves examples of autonomous weapons, lying dormant on the sea floor until their sensors detected the magnetic signature and acoustic noise of passing vessels, at which point they detonated automatically. Submarine warfare had destroyed most of Japan's long-range merchant fleet, cutting off raw material supplies essential to industrial production. The guided missile added another layer to this comprehensive interdiction campaign. The missile's direct contribution in terms of ships actually sunk was minimal, just 3 small vessels confirmed destroyed. But its psychological impact multiplied its effectiveness across all American operations. Japanese merchant captains became reluctant to sail even in waters where no guided missile-equipped squadrons were known to operate. The mere possibility of encountering these weapons added to the paralysis gripping Japanese maritime logistics. Ships that stayed in port due to fear of advanced weapons were neutralized just as effectively as ships actually sunk, but at no cost to American forces. American intelligence operations deliberately enhanced this psychological warfare effect. Information about the guided weapons was allowed to reach Japanese forces through various channels. Captured documents contained references to thinking bombs and robot missiles. Radio broadcasts announced American technological achievements, sometimes exaggerating capabilities to increase fear. Most effectively, survivors of guided weapon attacks were sometimes allowed to escape, ensuring they would carry their confused and frightening experiences back to their units, where the stories would spread and amplify. The weapon itself represented remarkable achievement, but also revealed the inherent limitations of 1940s technology. The analog computer that guided it consisted of vacuum tubes prone to failure from vibration, temperature, and simple age. Mechanical servos required precise calibration and could fail if impacted or jarred. The radar system was easily confused by environmental factors like rain, sea clutter, and radar returns from land masses. Success required near-perfect conditions, clear weather, isolated targets away from coastlines, and functioning electronics throughout the missile's flight. These stringent requirements help explain the modest combat record. Of approximately 100 missiles fired in combat operations, only a handful achieved hits. The weapon worked best against stationary or slow-moving targets in open water, far from land masses that might generate confusing radar returns. Fast-moving targets, targets in congested waters with many radar contacts, targets near coastlines, or operations in poor weather often resulted in missiles that missed or failed to engage entirely. The technology worked, but only under a relatively narrow range of conditions. Yet even this limited success proved the fundamental concept. Autonomous weapons were possible. Machines could find and destroy targets without human guidance after release. Every guided missile program that followed built directly on lessons learned from this first operational deployment. Engineers identified critical technologies that needed improvement. Better radar discrimination to distinguish targets from background clutter, more reliable electronics that could function in harsh environments, improved servo mechanisms with greater reliability and less maintenance requirements. The weapon was less a finished system than a proof of concept that autonomous warfare was achievable. The final guided missile attack of World War II occurred on August 13, 1945, just 2 days before Japan announced its surrender. Aircraft from VPB-109, operating from newly captured bases in Okinawa, launched 2 missiles at targets believed to be Japanese vessels. Both missiles missed, a fitting bookend to a weapon system that promised revolutionary capabilities but delivered mixed results. Yet that mixed record masked the weapon's true significance. It wasn't about how many ships were sunk. It was about proving that a new type of warfare was possible. By war's end, approximately 420 of these missiles had been deployed to operational units in the Pacific Theater. Only about 100 were actually fired in combat. The remainder were returned to the United States after Japan's surrender, where they became subjects of extensive post-war testing that continued until 1948. These tests revealed sobering truths about the weapon's reliability and accuracy under various conditions. Performance that had seemed acceptable during wartime, when any hit was valuable, looked much less impressive when subjected to peacetime standards of evaluation. The Navy ultimately removed the weapon from inventory in the early 1950s as newer and more capable systems entered development. Yet declaring the weapon a failure as a combat system misses its success as a technological demonstrator. Every American guided missile that followed incorporated lessons from this pioneering program. The engineers who cut their teeth on these early autonomous weapons went on to lead development of Cold War missile systems that would define military strategy for decades. Dr. William McLean, who contributed to the guidance system development, later led the team that created the Sidewinder air-to-air missile, using principles and technologies proven by the earlier program. The institutional knowledge, the technical expertise, the systematic understanding of how to integrate sensors, computers, and control systems into autonomous weapons all flowed from this first operational deployment. Military historians debate the weapon's significance with reasonable arguments on both sides. The combat record was undeniably modest. 3 small vessels sunk hardly seems worth $12 million, and the massive engineering effort involved. Critics correctly point out that conventional bombing and torpedo attacks achieved vastly greater results at lower cost. A single successful torpedo bomber mission might sink more tonnage than the entire guided missile program destroyed. From a narrow cost-effectiveness standpoint, the investment seems questionable, but this accounting ignores what the program actually accomplished. It proved that guided weapons were practical, not just theoretical. It demonstrated that autonomous systems could function in combat, under real operational conditions, rather than controlled test environments. It showed that future warfare would depend as much on sensors and computers as on human skill and courage. The weapon was the first step toward precision-guided munitions that would revolutionize warfare in Vietnam, in the Gulf War, and in every conflict since. Every smart bomb, every cruise missile, every air-to-air missile traces its conceptual lineage back to these first primitive radar-guided weapons released over the Pacific Ocean in 1945. The weapon also demonstrated a crucial aspect of American industrial and military philosophy: the willingness to invest in revolutionary technology even when immediate returns were uncertain. While Japan struggled to maintain existing capabilities, America explored entirely new categories of weapons with unclear payoffs. This approach to innovation, this willingness to take technological risks and invest in long-term capabilities rather than just immediate needs, this more than any specific weapon system determined the war's outcome. Nations that invest only in proven technologies eventually find themselves facing enemies with capabilities they can't match. Japanese naval records from the spring and summer of 1945 reveal the confusion these attacks created. Reports describe guided torpedoes, though the attacks came from the air rather than submarines. Other accounts mention robot aircraft or drone planes, which was closer to reality. Some reports speculate about death rays or other science fiction weapons, because observers couldn't explain what they'd witnessed using familiar technological frameworks. This inability to understand the threat made developing countermeasures impossible. You can't defend against something you don't understand. Post-war interviews with Japanese naval officers who survived the war revealed the profound psychological impact of facing automated weapons. They understood being outproduced, they accepted being outgunned and outnumbered. These were concrete disadvantages that could be comprehended within traditional military frameworks. But being killed by thinking machines struck at fundamental assumptions about what warfare meant. Several officers described a feeling that they faced not merely superior technology, but a completely different conception of combat. The rules had changed in ways they couldn't adapt to. The Japanese Navy's Technical Bureau attempted to analyze the threat and develop countermeasures. Without captured examples or fundamental understanding of the underlying technologies, these efforts went nowhere. Proposals ranged from the practical to the desperate. Some suggested using smoke screens to confuse the weapon's radar guidance, which might have worked but required equipment and coordination Japan no longer had capacity to implement. More desperate proposals included sending suicide swimmers to intercept the weapons, using small boats to ram them, or positioning ships in ways that made them hard to distinguish from background radar clutter. None of these countermeasures were ever implemented before the war ended. The weapon's legacy runs through every modern precision munition. The concept of fire-and-forget engagement, where operators release weapons and immediately turn away while those weapons guide themselves to target, originated here. Autonomous target selection, where weapons choose which specific target to attack based on sensor data and internal logic, began here. Standoff attack, where launching platforms remain beyond enemy defensive range while their weapons close the distance autonomously. All these fundamental concepts of modern warfare trace back to this first guided missile. Modern anti-ship missiles like the Harpoon, the Exocet, and newer systems are direct descendants, incorporating the same basic concept with vastly improved technology. Digital computers replace analog circuits, transistors replace vacuum tubes, sophisticated signal processing algorithms replace simple radar seekers. But the fundamental idea remains unchanged. Release a weapon that will find and destroy its target without further human intervention. The humble guided missile of 1945 was the ancestor of every smart weapon that followed. The ethical questions raised by the weapon about automated killing, the removal of human decision-making from lethal force, and the psychological impact of fighting invisible enemies anticipated modern debates about drone warfare. This was the first weapon to kill without human guidance after launch, crossing a threshold that military ethicists are still grappling with 8 decades later. When machines can select and engage targets without human intervention, who bears moral responsibility for their actions? When technology negates human skill and courage, what role remains for warriors? When killing becomes automated and mathematical rather than personal, what happens to the meaning of warfare? These questions, first posed by this relatively primitive weapon with its vacuum tube guidance and analog computer, remain fundamentally unanswered. Every advance in autonomous weapon technology makes them more pressing, more immediate, more consequential. The debates about armed drones, about artificial intelligence in weapons systems, about removing humans from the decision loop in lethal force applications, these are all elaborations of questions that first arose in 1945 when a guided missile struck a Japanese patrol boat from beyond visual range. For the United States Navy, the weapon provided crucial lessons that informed every subsequent missile development program. The importance of reliable electronics that could function in harsh environmental conditions became a central design requirement. Effective target discrimination, the ability to distinguish desired targets from background clutter and non-targets, proved essential. Operational simplicity, making weapons that crews could use effectively without extensive specialized training, determined whether systems saw widespread deployment. All of these lessons emerged from the weapon's mixed combat record, saving years of development time and millions of dollars in future programs that learned from this pioneering effort. The program's statistics tell a story of ambitious goals and mixed achievement. Development from concept to combat deployment took approximately 36 months, remarkably fast given the revolutionary nature of the technology. Manufacturing approximately 3,000 units demonstrated American industrial capacity to produce complex weapons at scale. Deploying 420 to combat units showed commitment to operational testing. Firing 100 in actual combat operations provided real-world data about performance and limitations. Achieving 3 confirmed sinkings validated the concept even as it revealed shortcomings in execution. These numbers describe a weapon that achieved limited tactical success but enormous strategic importance. The specific ships destroyed mattered less than the technological path opened toward precision warfare. The weapon proved that guided munitions were not just theoretically possible, but practically achievable. It demonstrated that autonomous weapons could function in combat. It established technological foundations and institutional knowledge that would lead to ever more capable systems. The 3 ships sunk were almost beside the point. What mattered was proving that machines could wage war autonomously. For the Japanese sailors who faced these weapons, the experience was fundamentally disorienting and traumatic. They were fighting a war they understood against an enemy they could see, and suddenly that war included weapons that violated every assumption they held about naval combat. Death arrived from empty skies, delivered by machines that could somehow see in darkness and think faster than any human. They were the first warriors in history to face truly autonomous weapons, and their confusion and terror marked humanity's entry into a new age of warfare. Their experience, being hunted by thinking machines, would become increasingly common as the decades progressed and guided weapons became standard equipment for every modern military. The weapon didn't win the Pacific War. Victory came from overwhelming American industrial production, from superior logistics and supply lines, from breaking Japanese codes and intercepting their communications, from submarine warfare that strangled their maritime trade, and ultimately from atomic weapons that demonstrated a new and terrifying level of destructive power. The guided missile was a footnote to these decisive factors, but it was a footnote that pointed toward the future of warfare in ways that even atomic weapons didn't. Nuclear weapons represented the ultimate expression of destructive power, but they required human decisions at every stage. Guided weapons represented the beginning of machine autonomy in warfare, and that autonomy would grow with each technological generation. Today, debates about autonomous weapons, about armed drones, about artificial intelligence in military systems, about removing humans from the decision loop in lethal force applications, these debates are still wrestling with questions first raised by this weapon. The technology has advanced beyond recognition. Modern guided weapons use digital computers millions of times more powerful than those primitive analog circuits, sensors that can detect and classify targets with extraordinary precision, and artificial intelligence algorithms that approach human-level decision-making. But the fundamental ethical and strategic questions remain substantially unchanged. When machines can select and engage targets without human intervention after initial launch, who bears moral responsibility for their actions? Is it the politician who authorized military operations? The commander who deployed the weapons? The engineer who designed the guidance system? The operator who launched the weapon? Or is the question itself meaningless once we've created machines capable of autonomous killing? These questions have no clear answers, even though we've been creating increasingly capable autonomous weapons for 80 years. How do warriors maintain meaning and purpose when technology negates the skills they've spent lifetimes developing? What does courage mean when battles are fought from beyond visual range by sensors and weapons that require no bravery to operate? What happens to the warrior ethos, to military tradition, to the very conception of what it means to be a soldier or sailor when wars are fought by machines? The Japanese Navy, with its deep roots in samurai tradition and its emphasis on warrior spirit, faced these questions in their most acute form. Their entire military culture became obsolete overnight, rendered irrelevant by technologies they couldn't match. Modern militaries face similar challenges as automation progresses, even if the pace of change allows more gradual adaptation. What happens to warfare when killing becomes mathematical rather than personal? When decisions about life and death are made by algorithms processing sensor data rather than humans looking into each other's eyes? When battle becomes abstract, watched on screens, waged by remote control, does something essential about the human experience of conflict disappear? And if so, is that loss something to mourn or something to celebrate? Does removing human emotion from killing make warfare more terrible or less so? These questions, first posed in rudimentary form by this early guided weapon, become more pressing with each technological advance that takes us further from personal combat. The weapon achieved relatively little in terms of enemy vessels destroyed, perhaps a dozen ships if we count probable kills and damaged vessels alongside the 3 confirmed sinkings, but it opened a door that can never be closed. The age of thinking weapons had begun, and warfare would never return to what it had been. The Japanese sailors who died without ever seeing their attackers were the first casualties of automated warfare, but they would be far from the last. Their confusion and helplessness in the face of incomprehensible technology presaged every soldier since who has faced precision-guided weapons, every fighter pilot who has been shot down by missiles they never saw, every ship sunk by weapons fired from beyond the horizon. They discovered, in the most terrible way possible, that the future of war would belong not to the bravest warriors, but to the smartest weapons, not to those most willing to die, but to those most capable of killing without dying, not to human courage and skill, but to sensors and computers and algorithms. This was the fundamental transformation that the weapon represented, and its significance far exceeded its modest combat record. In that sense, this humble guided missile, with its vacuum tube electronics and its crude analog computer and its tendency to fail in humid conditions, may have been the most important weapon of World War II that almost nobody remembers. Its true impact wasn't measured in ships sunk, but in futures foreclosed and doors opened, in questions raised that remain unanswered, in a transformation of warfare that continues to accelerate 8 decades later.